Okay, last question then. Question 1J. Let the floor of x, that's how we call it, the floor of x denote the largest whole number that is less than or equal to x. For example, the floor of negative pi is negative 4. Well, that makes sense, right? Because pi is like 3 point something. So if you have negative 3 point something, what's the integer below it? Well, it's negative 4. Okay, a function f of x is defined as follows. If x is between 0 and 2, then f of x is some sort of logs with some floors. Okay, great. And f of x is 0 otherwise. Note that, for example, f of 1/2 is 4 over 3. Okay, they gave you an example even. So because when you chuck in x is 1/2, then log 2 of 1/2 is negative 1, right? So the floor of negative 1 is negative 1. Remember, you include the integer itself. Yeah, so you don't go to negative 2 here. You still take negative 1. So 3/4 to the negative 1 is 4 over 3. And the value of that integral with boundaries is what? Okay, we've done enough MAT questions to realize that we're not supposed to directly integrate this, of course. Yeah, normally the integrations that we get, normally they have boundaries, as in we're more interested in the area under the curves instead of integrating the actual function. Yeah? So let's draw the graph. How does the graph look like? Well, so first of all, when we draw graphs, we need axes, of course. Where's my pen gone? There we go. Axes. So 0 is here, 2 is here. All right, that's x, that's f of x. Okay, so the function is 0 otherwise. So let me just sketch lines there. Okay, so well, let's start from the right hand side. What happens when you get log 2 of 2, for example? Log 2 of 2, that's 1, right? And the floor of 1, well, it's 1, right? The floor of 1 is 1, so that would be 3/4 there. But then it excludes 2, right? The boundaries excludes 2, so let's consider a number slightly less than 2, shall we? Okay, let's consider a number slightly less than 2. Say, just anything very close to 2, 1.9999, say. Okay, then the floor of log 2, let's say 1.999, whatever, okay, well, not recurring because that's the same as 2, but something slightly less than 2, you get the idea. The floor of this would be 0. Yeah, it would be 0. So 3/4 to the 0, that's 1. Okay, and how long does this phenomenon last for? Well, it lasts until you have log 2 of 1, the floor of that is 0. Right? If you go anything below 1, then because log 2 of 1 is already 0, right? If you go slightly downwards, then because log is a decreasing function, then you go even lower, and your floor will become maybe negative 1 or negative 2 or whatsoever, right? So this phenomenon lasts until 1. Okay, so now let's think about the range of values such that the floor is negative 1. What's the lowest we can go? The lowest we can go is log 2 1/2, right? Because 2 to the negative 1 is 1/2. Okay, so 3/4 to the negative 1 is 4/3. So we're here. This is 1/2, this is 4/3. Okay, just for the sake of clarity, if you choose x between 1/2 and 1, then your floor must be negative 1. Your floor must be negative 1. Okay, so 3/4 to negative 1 is 4/3. And the same logic works. So next bit, it would be, what would it be? 16 over 9 maybe? 16 over 9, and you go from like 1/4 to 1/2. Okay, so, and then it extends to infinity, right? Because if you log a number very close to 0, you get negative, very big number. Yeah. So the rectangles actually sort of shoot up and up and up, up and up and up, but they get more and more narrow, and indeed the area converges. Yeah. Okay, so when you see these things which shoot up, the fact if it converges or not actually is quite analysis in some way, okay? But in this case it does, because you know that this is a geometric progression. How come, you're going to ask? How are these rectangles geometric progressions at all? Well, because every single time the base halves, right? The base halves, thanks to this log base 2, right? Log base 2, that's why the base halves here. Okay, and how about the height? Well, the height is multiplied by 4/3. Yeah, it's 4/3. Because every single time this power drops down by 1. If the power drops down by 1, this whole thing gets multiplied by 4/3. Okay, so now what? Let's start from the left hand side here, right hand side. Sorry. What's the area of this? Well, 1 times 1 is 1. Okay, and what's the common ratio? Well, we said the base gets halved and the height is 4/3. Right, same logic. What's the next one? 1 times half times 4/3, and again, times half times 4/3. That's our third rectangle. And so on and so on. You move your way to the left, closer and closer to 0. There are infinitely many rectangles, of course. All right, so this is a sum to infinity, right? So a over 1 minus r, so 1 over 1 minus, what's my r? Half times 4/3. Half times 4/3 is just 2/3. Yeah, 1 minus 2/3 is 1/3, and 1 divided by that is 3. All right, so we see, once you get the picture in your head and you can sketch it, then you'll be good. Yeah, I think the most confusing thing might be the floor thing, and then you still have to deal with logs inside. That might be daunting. But just draw the picture and you'll be good. All right, and it becomes a sum to infinity, which is lovely.